Hello. Let's see. Does that show up?
Yes, it does. We can see.
Great. Um, okay. Go away, little window. Okay. So hello. Welcome to my presentation. Today I'm going to talk about a module I wrote called the repartition module. I'll explain what it does, how it works, and why it can be helpful for a wide variety of projects. Um, So my name is Ryan Keck. I'm a software engineer working on our CUDA, a Python, and Chapel data analytics framework designed for interactive, large-scale data exploration. There was the talk yesterday by Amanda and Engen. Um, Hopefully you saw that. I work on a few different parts of the project, but one of my main areas of focus is performance optimization, figuring out how to make operations run faster or scale more effectively across many nodes. So before I started working on this project, there had already been some effort towards improving group by performance. And for numeric data types, things looked pretty good. But as you can see here, string group by performance still leaves some to be desired. I first noticed this issue while running our unit tests. There was a particular test working on a very small amount of data, but it was taking much longer than expected. When I looked closer, I realized that under the hood, it was performing several string group bys. And so as you can see, this is the benchmark for group by with strings. This comes from our CUDA nightly performance graphs. Seeing this by itself is maybe a little bit out of context, but many other functions operate at somewhere around 4 to 6 gigabytes per second at least. Um, and so at first I thought I could simply write a little bit of code to work around those group bys, but I'm sure as many of you know, you write a little bit of code and then turns into more code, and then you've got a whole bunch of code that you're writing and there's no end in sight. So that's kind of what led me down the path that became this project. So let's talk a little bit about how to distribute a computational problem. This might be a little bit low level for some of you, but anyways, some problems parallelize very naturally, kind of like on the left here, where um, you might, for example, you might consider multiplying a vector by a scalar, and every element can be handled independently, and you just go do everything on your own data, and it just works very nicely. There's not a lot of communication between nodes, and the work scales really well across all the locales. In other cases, it's not that simple, and that's kind of like the other image on the right. The data you need to operate on isn't local, or it needs to be combined with data that's distributed elsewhere. In those cases, you have to move data across your locales, and how you organize or reorganize that data can have a huge impact on performance. For example, you can consider taking the union of two sets. Um, if the memory of both sets is distributed, um, we have to find some way to make sure that elements get deduplicated on the same locale. Um, because, you might have one string in one place on one locale, and you might have that same string in some other locale. And so you kind of have to find some way to map everything the right way, but still kind of balance across your locales. So how can we make sure that everything that needs to go to the same place goes where it belongs? So one answer that I came across was hash-based sharding. Um, so computing a hash of each element and mod it by the number of locales, assuming your data is random enough, this should balance the computational work evenly across locales. For example, this solves the problem of set unions because the same value gets mapped to the same locale where it can be deduplicated. So there are some potential drawbacks. So someone could construct data that hashes poorly, but in realistic scenarios, randomness usually evens things out. And if all the data is identical, even hashing can't balance it, though in most real world data, that's not really an issue. So for now, let's just assume that everything looks reasonably random and we don't have people trying to sabotage us. So this is where the repartitioning module comes in. The idea is that you have your data split up across locales. You mark each value with the locale that it's going to, pass all that into the appropriate function, and it hands back an object with your data redistributed accordingly. I'm even including like some functions that will just hash the data for you, so you don't even have to mark it. You just have to say, here you go, here's a bunch of data, just send it. So once I had the overall approach, I still had a few important design decisions to make. Um, as some people have talked about in other talks today and yesterday, I think you can do source or destination aggregators or even like bulk transfer. Aggregators are great if you know ahead of time where your data is headed. But in this case, it's kind of hard to predict exactly like which index your data is going to land in. So I decided to go with bulk transfer, which kind of comes with this extra trade-off of like a little bit of like this extra copy that you have to make of your data. But theoretically, I think it's just one copy, so it's not like huge. Um, the second decision was between lists and arrays. Lists are nice from a memory perspective because each locale can have a differently sized list. Because even if you try to balance your data, some locales are going to have more data than others. Um, so, it's a little bit annoying to have to do like this little padding on the end. Um, so the flexibility means that you don't have to allocate unnecessary memory, which is nice. But um, I know I put in my abstract, I think that I was using lists, but I found that lists are kind of expensive to operate on directly. So you have like this performance cost and some extra copies, I think. Arrays are faster and let you insert data directly, but they require pre-allocating memory, which may be wasted if the distribution is uneven. Um, and if you're not careful, the domain can end up being distributed in an inefficient way. So it kind of raises this question of like, do you want to do memory inefficiency, or do you want to like sacrifice some performance? And that was kind of an unhappy question. So then came inner arrays, which kind of give us the best of both worlds, flexibility in memory usage and efficient access. You can see it's basically just an array wrapper. Um, and thank you so much, Engin, for this approach. He came up with the inner array record. So um, basically, it allows us to just have this array object, which doesn't necessarily have to have the same uh, memory allocated to each locale. And so you just overwrite it inside of a coforall and create a reference to the R inside, and everything looks good. So here's the com diagnostics results. This isn't exactly performance, but it kind of gives you an idea of the possible performance. Um, so um, yeah, you can here, let me just highlight a few things. Oh, and also I want to say, so the test was very specific. I generated n strings randomly between 1 and 16 bytes and n over 2 indices to grab, and it was just like an array indexing thing. Um, so using the smaller indexing array to index into the larger array. And I ran this on 8 locales. It tended to be the case that locale 0 would look like one thing and all the other locales would look very similar to each other. Um, main is the current approach with aggregators and branches using my repartition code. Um, and come on, there we go. Circles. Okay. So as n scales, the number of gets, puts, and execute ons increases for mains code, but for mine, you see there's not really any change. It doesn't mean that performance will be better. There's still on locale computations being run, but it does mean that there's potential for something there, I think. And this isn't group by, which is really complicated, and I'm building towards it, I promise. So anyways, to wrap up, the repartition module gives us a flexible way to reorganize data across locales, reducing communication overhead and opening the door for more scalable performance. There's still more to explore, especially in more complex operations like group by, but I think this lays a strong foundation for future optimization. And thank you for your attention. And I think I'm out of time, but if there's time for questions, then happy to answer.